My name is Robert Shapton. I'm Managing Director of Tailor-Made Systems. We design and manufacture airfield lighting, test and inspection products and services. We're very proud to present today's AGL Safe Working webinar, an extremely important topic, and we have a super expert panel today with us to present the topic and answer your questions. I have with me, of course, as usual, Keith Costel, Director of Tailor-Made Systems Training Solutions, worldwide authority on AGL and ground traffic management, and has probably trained a great number of the participants on today's webinar in the past. With Tony Smith, I'm very proud to have here, an applied physicist and fellow of the Royal Aeronautical Society, inventor of the PAPI. I was just looking at your CV today, Tony, and I was thinking possibly we should do a webinar, a lecture, if you would kindly do a lecture for us on your experiences, on your life in airfield lighting, and you can tell us all about how what you've done, how you've done it, because I genuinely think the audience would be absolutely fascinated, as I am, which is why if I ever have any questions on any topic whatsoever to do with airfield lighting, I would, I have no hesitation in picking up the phone to you, and very grateful for your answers. Steve, not at all. Steve Martin has also kindly agreed to join us today. Well known to very many of you, I know. He's an well-known airfield lighting tutor and trainer with over 40 years delivering safety and competence training in the industry. And he currently represents the UK on the TC97 AGL committee. So welcome to Steve. And I'd also just like to give a special mention to Felicity Parks, our training manager, and Damon Creed, our marketing manager, who've done a lot of work behind the scenes to put together today's presentation. So without any further ado, I'd like to hand over to you now, Keith.
Why today's webinar on safety? Well, we want to make sure that we, as engineers and technicians who are working on the ground, remain safe and alive. Because in previous webinars, we've spoken all about maintenance, compliance, etc. But AGL safety is something, and it is AGL airfield ground lighting, aeronautical ground lighting, electrical safety, because it's an electrical system. And this electrical system will kill or will seriously injure you. And so previously we've concentrated on equipment and facilities. Now we're concentrating on us. And here is a press report from the USA, that an electrician who was working on the airfield was killed. And he was 61 years old. He was pronounced dead on the scene after being electrocuted while working on taxiway lights. Why? We don't know, but we can imagine why this has happened. And when we say imagine, because we also can look at ourselves and say, could this happen to me? Have I had a shock from AGL? And if not, that means I have already gone through all the safe working procedure processes that we need to do. So this is what it's all about. But AGL will kill. We mentioned earlier, current kills, voltage burns. We have voltages which will burn. We have current that will kill. And the safety procedures and the safety processes and equipment that we have is designed so that we will minimize the possibility of serious injury, a shock, electric shock, etc. But unfortunately, the 6.6 amp system is not, as we know, constant voltage in building technologies, which has lots and lots of safety processes and safety equipment in place. Not so, it's very minimal out on the airfield. we really need to ensure that we understand and we know and we are competent and confident to be able to work. So let us remind ourselves what an AGL circuit, an airfield ground lighting circuit looks like. There is a control system, there is the power, and there are the lighting fixtures out in the field. And it's those lighting fixtures out in the field and the power unit, the constant current regulator, which is the key issues that we're talking about today. And in the field, we have the secondary circuit, which is where we plug our lights into. And we have the primary circuit, which is the circuit that delivers the power out into the field. The secondary circuit is normally at a low voltage, but it is at 6.6 amps, because we are talking about the traditional 6.6 amp systems. There are other systems in the marketplace and out in operation, but today we're talking about the key 6.6 amp system, which is fundamentally the danger. We have 12 amp systems in the industry, we have 20 amp systems in the industry. So the discussions that we have on the 6.6 amps are equally applicable to the 12 amp and the 20 amp systems. The primary circuit is where we connect from the power unit, which is in the substation, switch room, vault, whatever you want to call the building, the constant current regulator, and there we have voltages in a 6.6 amp systems up to 4,545 volts RMS, and much higher before a CCR will trip out in a fault condition. But we also must remember that we add also a lot of equipment into the field. And this equipment is for individual light switching, which is part of an ASMEX, a surface movement guidance equipment. So just to remind ourselves, this is an added feature that exists today in many, many airports. I'm not going to go into the technical detail of it, but just to remind you, it's not just a standard power unit, lights, and a distribution system. It is a control system as well. In that, going back to the substation, the vault, the switch room, then we want to build in, wherever possible, some protective devices. So we have a protective device for the incoming power supply to that constant current regulator. And we have a facility to be able to isolate and to earth down the field circuit in the output side of the constant current regulator. In the output side, which is what we know is the danger, because that's where we are going to actually do some work out in the field on, then the output disconnecting device is a very, very useful piece of equipment to have. It can be attached and part of the CCR, or it could be in a separate place in the substation. This is what the equipment looks like. The incoming protected device, this is the safety equipment. We have the output disconnecting device, which connects between the CCR and the field. And this is one model. And of course, in the middle of this is the constant current regulator. They range from a whole range of sizes, from 2.5 kVA up to 30 kVA, traditionally in a 6.6 amp system. And at 30 kVA, when it's fully loaded, we could have 4,545 volts RMS. And the CCR is only designed to trip out when the voltage, when the load, rather than the voltage, the load then goes up in the field, maybe from an open circuit, and when the output voltage, the CCR, is a constant current machine. Therefore, it stabilizes the current at whatever intensity level is chosen, and it adjusts the voltage and adjusts the voltage. And at a value of a load, like an open circuit, the load goes to infinity, then the CCR says, oh, the load has changed. I'll just ramp up my output voltage. And at two times, 4,545 volts, it's designed to trip out. But there is a time frame, time constant associated with that. So it could be much higher before it actually trips out. So going back to our field circuit, we have our primary circuit, we have our secondary circuit, and we have the light fittings, fixtures, call it what you like, but that is the lighting fixture that we plug into the secondary circuit. We have an isolating transformer. Don't be misled by the name. It does not isolate in the event of a problem. It is a series current transformer, a one-to-one series current transformer. It is only to isolate the secondary circuit from the primary circuit, does not provide safe isolation in terms of fault conditions, just to beware. So what are fault conditions? Well, on Earth, our cables live in the ground, in docks or directly buried. So we have an earth fault potential because we have to connect these transformers to the distribution network, the primary circuit. And these connectors are designed to be watertight, but over time, deteriorate. And this is the potential where we can get leaks, earth leakage. So we do have earth leakage. We have an allowable earth leakage in the system by the nature of where it lives. But it is a fault. Now, just remember, one earth in a field circuit has no operational effect on the illumination of the lights because this is a closed loop circuit in normal operation. And therefore, one earth has no operational effect on the illumination of the lights. It's only when a second earth comes. Therefore, what could happen? To give us an earth fault, it's low insulation resistance. Now, this is not a training course, it's an awareness webinar. So what we do is frequently and regularly measure the insulation resistance of our field circuit. And when we frequently and measure the insulation resistance of our field circuit, we need to take the records and we do it against a standard. And that standard is associated with allowable earth leakage. But we would test it for compliance at 5,000 volts. And the reason why we're testing it for compliance at 5,000 volts with an appropriate insulation resistance tester, commonly called the mega test, then the reason why we do that is because the equipment, the isolating transformer, the connectors, the cable, whatever kind of cable we've got, it's usually a 6mm square single core current carrying conductor, insulated, possibly with PVC, etc., but commonly with XLPE, cross-linked polyethylene insulation. But we want to ensure that the security and the integrity of that circuit as a closed loop remains. When it doesn't, it's usually water or fluid leakage into a joint or a failure of the isolating transformer. And when we have that situation, we have to remember, if we put our fingers into that field circuit, a live circuit, we are a human being, and a human being cannot let go when there is 10 milliamps and above. And we have got 6.6 amps, up to 6.6 amps. availability. So there is potential danger there. So here is a scenario, one scenario I'm going to show. I'm not going to go into the detail of it. I'm going to show you this. And this is what we think happens when somebody gets seriously injured or killed when they are touching or trying to change a lamp, for example, a tungsten halogen lamp in a live fixture, in a fixture on a live circuit. What can happen? Let us say water leakage inside that transformer. So now the primary is connected to the secondary. And there is already an earth fault in the circuit. And you haven't done it. You haven't rectified it because there's no operational effect. So, oh, well, we'll do it tomorrow. Oh, we'll do it next week. The thing is, we could be the second earth. So we give an alternative path for this current. So it goes this route. So if we have put our changing our lamp in a damp environment, etc., and there's already an earth fault, this is the possible alternative and parallel path, because we've still got this link, but now we are now joining ourselves to the primary circuit. So we are the alternative parallel path. Now that could be electric shock, or depending on that current, death. One option, and what has happened in many cases around the world. So do not believe it will not happen to you. Potentially, it could. So that's one scenario. There are other scenarios, of course. So this is not exhaustive. There are other issues which can create issues. As the isolating transformer itself, this transformer that we've got many of them out in the field, does it have an earth connection to, on its output on its secondary side or not? Because the two options are available. If there is an earth connection, there is, and leakage occurs here, there is already an alternative path rather than through the human being. So there's merits on why the use of earth transformers and non-earth transformers, which can exist. Is that a lamp, has the lamp actually failed? Because when the lamp actually fails, this is in open circuit. So if this is an open circuit, then this isolating transformer can go into saturation. When it goes into saturation, it's no longer a transformer. So now we have the potential of a higher voltage on the secondary side. So there's just some other examples what can happen. And if you are going to work, and I'm going to bring this straight into if we are going to ignore safety regulations and safety procedures and disconnect a live airfield ground lighting primary circuit, you could be injured or killed because it's an unseen threat. And it's only when you make the mistake and work on a live circuit and it can hurt, and hurt in a big way. And these are some injuries created by AGL. Pictures I've assembled around over many years, but I'm not going to give any excuse for showing them. These are AGL injuries created by different things. So coming back to this gentleman in Westchester who was killed working on a AGL on a taxiway light, we have to say, why did it happen? Well, we know fundamentally why. He worked on a live circuit. The defect in that live circuit I don't know. But it has happened, and it's happened many times before, and we do not want it to be you, because you, and I have to say to you, have you ever had an electric shock of an AGL lighting fixture? If so, why? If you're still here to answer that question, you're one of the lucky ones. This poor gentleman was an unlucky one. So injury is death. But we have personal injury created by shock, burning, fire from electrical origin, electrical arcing, or even explosions. This happens. This really does happen. Why? Fundamentally, an error, a defect piece of equipment, or we have not rectified earths in our field. So you have to go back to your airports and you say, do I have earths on my circuits anywhere at all? If you have, why have you not rectified them? So we have direct hazards. This is a hazard. And we have these voltages, and the law in many countries will say when you are working on an electrical system where the voltages exist on that electrical systems greater than 1,000 volts, then it is mandatory to adopt high voltage safe working procedures. And therefore, you know, it's important. But I'm not going to go into the detail. You can look at this presentation afterwards. And so we have direct hazards and we have indirect hazards. One indirect hazard is pressure. You know very well if something goes wrong in the field, it needs to be rectified. Operations or air traffic control, we get the phone call, can I go out there? Yes. How long have I got? 30 minutes. And you get out there and you know it's going to take more than 30 minutes. You're already working under pressure. When you work under pressure, that's when you're liable to make a mistake. That's where you're liable to say, let's change this on this live circuit. It's only low voltage. It's a secondary circuit. I'll be fine. Bang. We've gone. So we do risk assessments associated with the work, and Steve's going to talk about it in a minute. Here is a typical aviation airside risk assessment where you define the severity of the risk and the probability of it happening. And we have then 3 levels that we decide, is it high risk, medium risk, or low risk? And this is a typical chart for a risk assessment, which then bleeds us on to the standards and us, competency. We have to abide by standards. And this is where, Steve, I think it's a good time for you to come in, I think.
Okay, thank you, Keith. Yep, would you like to go on to the next slide for me? Okay, yeah. So as Keith has outlined, these AGL systems are a bit different to anything else, and we really need to know what we're doing. So the 2 key areas, I think, are ensuring that the people are competent, so they know what they're working on and understand the hazards, and that we have a plan. As with most things, having all the players, and having footballers out there, but having a lot of good players is great, but if you don't have a plan to bring it all together, it won't work. So we need to look at both. Based on our sort of UK systems, I've put up a couple of documents that are worth looking at for further guidance. These are guidance documents. You can do what you want, but it's always, I think, better to have a plan that's somebody else has had a look at to start with, rather than just make something up on the foot. So 2 good documents. The BSEN 61821 is the same, practically the same as the IEC document Keith's been talking about, but a lot of good guidance in there, and it's the only document that's actually specifically written for maintaining AGL circuits, and a lot of good advice in there. And then the other one, Electricity at Work, produced by the Health and Safety Executive in UK, HSG 85, safe working practices, not specifically written for AGL, but it's got very good guidance on working on electrical systems, and it's nice and clear and straightforward, and it's got pictures, which is always good for engineers. We don't like reading lots of detail, certainly don't like reading all the instructions, but this has got some good pictures in. Okay, Keith, move on to the next one. Yep, so first thing, determine the competence of persons. Keith and I have been working for 20 odd years trying to establish a standard set of competencies for work on AGL systems. Producing the competencies isn't hard, but getting people to adopt them is more difficult. This is again a set of guidance produced by the Health and Safety Executive to meet the UK regulations, Regulation 16, which says we shouldn't be working on systems unless we're competent. Doesn't say you've got to be expert. It's making sure that you've got the appropriate requirements for the task. So adequate knowledge of electricity. Yeah, we've all probably at this thing got that. Adequate experience of electrical work. So we've done a bit of work on it. Yeah, should be okay. Adequate understanding of the system we worked on and practical experience of that class of system. Once we start talking about AGL systems, that's the difficult bit. They're completely different to everything else we've ever worked on. These circuits are designed to stay on, whereas we're used to circuits these days turning off automatically if we have an earth fault. These are designed to stay on, so we have to be aware of that. Understanding the hazards which may arise during the work and the precautions we need to take. Yeah, we need to understand what the specific hazards are so we can deal with them. And most important one, the ability to recognise at all times whether it's safe for work to continue. As Keith's already highlighted, you're under pressure when you're out there, and the sort of danger is that we're going to carry on, we've got to get the job done. So we'll keep doing it, we'll keep going. Sometimes you just have to stop and say, no, we can't do this in the time, we're going to have to come off and go back again. So that's a good little chart to use if you're thinking about, can I work on these systems or not? Okay, next one, Keith. Yep, so within the IEC document, it puts the onus on the individual aerodromes, airports, to determine what needs to be authorised, who's going to do the authorisation, what written permissions are required, and who's going to control what happens. So again, down to you. You can always, or your management can decide, we're going to do it this way or we're going to do it that way. However, in the last part of the IEC 61821, they have put in Annex A, a method that can be used, and it is one that we have used in UK successfully for about at least 30 years. Certainly the UK Ministry of Defence and also a lot of the civil airports use this system. Okay, next slide, please. Yeah, when you see 4 people, some people say, oh, we haven't got that many people on the airport, we couldn't do this. You don't need 4 people to do the work. This is different roles rather than necessarily different people. In IEC 61821, it says if you're working on a primary circuit because of the dangers involved, you really need a minimum of 2 people, unless you come up with a risk assessment that says, no, we don't need them, but you generally need 2. The gentleman on the left-hand side, the authorised engineer, we'll come on to him later, but he has no direct involvement in the work activities. To do the job, we need an authorised person who has the knowledge to safely isolate the circuit. And then we have to have a skilled person in charge who knows about the actual work task. The accompanying safety person is only a temporary function while the authorised person is isolating the high voltage circuit for his safety. Can and usually is done by the skilled person or person in charge, as long as they're suitably qualified, know where to turn the system off. We've got a chart coming up in a second just to illustrate that the functions of these jobs. Okay, Keith, next one. Yeah, so this is a little chart showing the 5 functions and who's required to do each task. So the safe isolation of the high-risk system, which includes the planning, the isolation, the proving the circuit dead, the earthing, and the issue of the safety document, that's the responsibility of the authorised person. So he's suitably qualified, experienced, and understands what's required to make the circuit safe. He will then hand the circuit over once it's safe to the person in charge, who, again, understands what the work's involved, but he also takes the responsibility for making sure that safety is maintained while the work's being done. Okay, he's going to be a skilled person anyway. He's going to understand the tasks involved. If he needs extra assistance, then he might have somebody else with him who is a skilled person who also understands the work and the task. As I say, the role of the accompanying safety person assisting with the prevention of harm or injury is only required while sort of most dangerous parts of the task for the AP, the proving dead and the earthing, because until we've done that, we've got a live circuit there, or potentially a live circuit there that could be at several thousand volts. And then the one at the bottom, the management of the safe system of work, the appointment and monitoring of the APs and the audit of safe systems, the authorizing engineer, he's the person with the sort of overall responsibility for making sure that the authorized person and the others are suitably qualified, suitably competent. He'll appoint them in the first place, having tested them and checked their credentials. He'll make sure there's a safe system in place, so there is a plan for them to follow. And he'll also carry out regular audits on the system to make sure that the system is working as it should be and that the people are actually carrying out the tasks as they should be. So that's a fairly comprehensive system. It looks like it's sort of quite involved, but it does work. It's sort of belt and braces, but it does work. And I'm pleased to report that certainly so far, we've had no incidents in the UK that have resulted in fatalities while working on AGL primary circuits. We may just be lucky, but hopefully some of this safe system is contributing to that as well. Okay, Keith, next slide. There you are. This is one way of doing it. This is produced from the health and safety document, HSG 85. This is a flow chart that you can follow for making the system safe. So the first thing it says is identify the circuit or equipment to be worked on. With AGL, it's quite difficult to make sure we've got the right circuit because we've a lot of circuits out there, either buried in the soft in some instances or in ducts. We may have color coding, but that's not 100% reliable. So we've got to make sure we come up with a way of checking we've got the right circuit first. Once we've done that, we can then cut off the supply, so remove the incoming supply, isolate and secure the isolation. So we want to make sure not only is it turned off, but nobody can turn it back on again while we're out there in the field working on it. Underneath these, I should point out that the bit in green that says regulation, that's the electricity of work regulations you're complying with. The next bit says retain the keys. So usually for isolation purposes, we use what we call a safety lock, which only has one key. It may well be red in color to identify it. We want to make sure that that key is secure, so nobody can actually turn it back on by accident. Post caution and danger notices, they're warning other people that something's actually happening. The caution will say that people are working on this equipment, and the danger notices will warn of any adjacent live circuits that might get confused with. We then require to prove the circuit or equipment dead before we put our hands on it. It's always a good idea when we've got high voltages and currents like we have on these circuits to make sure before we touch it that it is in fact dead. Doing that with AGL is quite difficult because all the equipment is mainly designed for being installed out in the field, being waterproof to prevent sort of water ingress. So getting access is difficult. Usually then the only point we can do that is, as Keith highlighted, the output disconnecting device on the output of the CCR. We can usually, once we've isolated the circuit, get to that point and put a tester in there. Once we've done that, we then want to earth the circuit, because even if we've got the right circuit isolated, we may have other cables, other circuits running adjacent to there, and we can get induced voltages of 100, 150 volts easily on our circuit if we don't earth it down. We have long runs of cable, several kilometers of cable, and they can pick up induced voltages. If we have got any adjacent live equipment, we need to take precautions. So we warn people that adjacent equipment might be live. Issue a permit to work. Permit to work is a safety document. This is pretty easy. Do we really need a safety document? Having a document sort of focuses everybody's mind. we hand over the responsibility from the AP to the person in charge. And then sort of if unfortunately anything goes wrong, there is something there to say what we should have been doing. And then we can see, has it been deviated from? We've got something to show of what we've done. And then we could apply local earths as well if we think that's necessary to prevent any charge build-up. So if we follow that system, follow that step by step, we should have a safe situation before we start the work. Okay, Keith? Yeah, doesn't have to be anything complicated. This is a sort of a memory checklist that you can have there when you're thinking about it. So the preparation steps, we need the risk assessment that Keith talked about earlier to make sure that we've got everything, we've covered everything and thought about it. We then need a method statement or safety program to make sure that we're, as the AP, making the thing safe. We've thought it through and we've covered all the bases. In the old days, we used to sort of rough this out on the back of a cigarette packet. Now everybody stopped smoking these days. We've had to do it a bit more formal. About 30 years ago now, the UK government organisation that was looking after the MOD airfields at the time came up with the idea of a method statement with a diagram on it to show how the installation would be when it had been made safe. And we still use that, and it's proved to be a really useful thing. I'll show you an example in a minute. Then we need to do the positive identification of the circuit. This is the hardest bit and normally involves going out in the field first, switching the circuit so that we can find out we've got the right one. We then need to isolate the low voltage supply and also the constant current circuit. So we make sure there is no danger to the people in the field. Prove dead, the output disconnecting device, and if possible at the place of work. That's usually difficult to do if it's in the field, but if it's inside in the AGL switch room substation, then that is possible, and we'd always want to put a tester on before we put our hands on anything. Then we can earth the circuit, either the field circuit if we're working in the field, or if we're working in the AGL switch room vault, then we may be able to earth the power supply equipment to prevent any charge build-up. And then again, issue the safety document. It's two examples there: permit to work or a sanction to test, depending on what the task is we're going to do. Other people use things like standard operating procedures, specific written instructions, standard instructions, simple as possible, but just a written document demonstrating that we've actually thought about it and we're handing over the process. Okay, next slide. Yeah, so this is an example of a safety program. It's a diagram of how the installation will be once the circuit's been made safe. So the scenario in this is that they're changing a transformer, failed series circuit transformer, which, as Keith says, happens quite a bit, unfortunately. So that's the point of work. We've positively identified it beforehand. We've got the circuit isolated at the output disconnecting device, CTP, as it's mentioned in here, and we've moved the links to the earth position, and we'll have had that locked with a safety lock and a caution sign. And at the top, the LV supply, incoming LV supply, has also been isolated and locked off as well. So that diagram says a lot. If you're the person checking before the thing is actually carried out, if the diagram looks right, then that probably is going to be good. And also these days, it's usually shown to the person in charge, and they usually initial to say they've seen it, because if you've carried out the isolations as you've said you were going to do, then they know that you've got it right. Okay. This is a gentleman carrying out positive identification. So he's got a clamp on ammeter inside the pit, obviously filled with water, on the circuit that is going to be worked on. There is somebody else in the AGL switch room switching the CCR through at least 3 different brilliancy levels, checking that what's on the meter corresponds with what's on the CCR in the switch room, and then they know they've got the, as best they can, they've got the right circuit. Okay, Keith. Yeah, so this, we can then isolate the circuit. So this is one LV switch disconnector, but it's in the off position, safety lock. And this one's red for so clarification that what it's doing is being used for safety. The key's been removed and we're going to put that somewhere safe. And then we've got a caution sign on there that tells anybody that there's people working on the equipment and they shouldn't interfere with it. So isolate, disconnect and separate from electrical equipment from all normal sources of energy, such a way that the disconnection and separation is secure. It's the secure bit that's important. Okay, next step. So proving dead, that the output disconnecting device, once the circuit's isolated, we can remove the plug. We can get access to the terminals using a suitable voltage tester, such as the one in the picture here. We can safely then test to prove it's dead. Okay, next bit. And then once we know it's dead, we can move the link to the field earth position, put it back in. We've now earthed that field circuit. So we know that our circuit is down to earth, should be at sort of zero potential or close to it. We can lock the actual cabinet with another safety lock and another sign. So we've secured, so we've got the LV supply and the outgoing HV supply from the CCR locked off, isolated and earthed where we can. So again, as secure a measure as possible. Okay, next slide. The keys, we've now got 2 safety lock keys. If we kept them in our pocket, there is a chance that 1, we could lose them, and 2, we could turn the circuit back on. So for the security of the person doing the job, we put the 2 keys into a lockbox and lock them in, and that box has got 2 keys as well. So next slide, Keith. There we are. So we have a key to the safety key box for the person in charge, and a key to the key box for the authorized person. So AP keeps his key, and the person in charge key is issued to the person in charge with the safety document. So the AP there is just finishing signing the safety document. That will be handed over at the point of work to the person in charge. He's also got the security of knowing he's got the safety key box key. So without sort of damaging the box, there is no way anybody can get back in, get the keys to the safety locks and remove those while he's doing the work. Okay, so like I say, not the only way of doing it, but it's a system that works or seems to work. We've got a donation here by Birmingham Airport into their system, which is based on a 9-step system. So again, step 1, prepare the safety program. So they do the same thing. They prepare the safety program, get it countersigned. They obtain permission from air traffic, having worked out how long it's going to take them to do the job, carry out correct identification. They isolate and fix the signs. Then they prove dead and earth at the output disconnecting device. They'll then issue the permit to work or other safety document, confirm dead at the point of work, if possible, undertake the work. And then when work's complete, they'll check the work, agree that the thing's been completed, and then the person in charge will return the safety document to the authorized person, who can then cancel that document and then start to restore the installation of the circuit. Okay, thank you very much for listening. Back to you, Keith.
Hello, yes. So now we're coming on to our Q&A, and I think, Robert, you've been monitoring the
yes, we've had a
question
number of
and answers, so maybe it's a good time to bring up some questions.
So thank you, Keith. Thank you, Steve. Excellent presentation, very informative and very, very important for all of us, for our own safety and the safety of our colleagues. So some questions have come up. The first question I have is from Nick, who thanks you for today's wonderful presentation. So thank you for that, Nick. My question is, what would be the minimum fibrillation sufficient enough to throw off a technician working out in the field? What installation imperfections would occasion this?
Maybe I can jump in there initially.
Yeah.
The situation is that, which is the slide I showed during my part of the presentation, is when there is already an earth in the field circuit. And we know that when there is one earth in the field, the primary field circuit, then it has no operational effect on the lights. But a light may be shown to be out. But if that light, a single light is out in the field, and there is already an earth on the field circuit, then it may, the natural assumption, it is the lamp has blown. It may well be, as I said, it may well be the isolated transformer that has leaked. And therefore, if it's no longer a transformer, then the possibility is the lamp is not going to illuminate or has has created it to fail. And so that scenario, and it is that actual situation that if you touch that live circuit, then we know at 10 milliamps we can't let go. But we don't know what that current is going to be, because current takes the path of least resistance. Now, in a human being, our resistance to current flow is somewhere, I don't know, 10 ohms or more. Remember, depending, every human being is different. And we're out in the field, possibly in hot conditions where we're sweating, you know, perspiring to some people's words. It could be raining, etc. out there. We could be wet. So our resistance as a human being to current flow potentially is very low. So current will say, I'm going to take the path of least resistance. I'm going to go that particular way. So that actual value of current that will blow someone off, it is very debatable. In excess of 10 milliamps is the danger, because that's when we cannot let go. So that's all I'm going to say, because there is no fixed value of at what current value you get blown off it. You either are holding it, or you stay holding it and the current flows through you, and potentially your heart gives way, as we've shown on the pictures in one of the presentation slides, or you get blown off. But if you get blown off, the chances are you've got burning. So it's a mixture of voltage and current, which is the key issue.
Thank you, Keith. Nick has followed this up with a question saying, with regards AGL isolation, what would be the minimum recommended value as well as the lowest below which the CCR may not be switched on?
I don't really understand that
I
question fully.
I think, Keith, what he's asking is, you talked about when you were testing the circuit with faults and things, various insulation resistance values. It's an interesting question, and it's one that's being debated by the IEC committee at the moment, trying to come up with a standard value. In constant voltage installations, certainly in UK, we have a sort of a minimum of 1 megohm. If it goes below 1 megohm, you should turn the circuit off and start fault finding. That is the current suggestion for AGL circuits, that if it drops below 1 megohm, then you should sort of turn it off. That hasn't been confirmed yet. UK MOD have a formula for calculating at what sort of value you should turn it off and start working, and that's generally down in the K ohms. So you're probably talking about about 0.2 megohms is the sort of value that you'll usually sort of calculate for that. So there is no set value at the moment, but obviously once it starts getting down, the lower it is, the more risk there is. So 1 megohm, 1 megohm is a good sort of rule of thumb, I would say. If it's below that, then you certainly should be fault finding on it and trying to work out why.
And I think the earth fault detection on a CCR facility helps us to identify, us all to identify when there is a changing value of that insulation resistance, because an earth leakage just doesn't happen as suddenly it's direct short to earth. It could be a high resistance short to earth. So progressively, what happens is that the insulation resistance value falls down. So we calculate the acceptable earth leakage required with the 1 microamp for every 100 meters of primary cable, and 2 microamps for every transformer that we have in our particular circuit. So we have something to calculate an acceptable level initially. But then, of course, over time, it will gradually reduce. And as it reduces, then I recall then in the UK MOD, we had a level of calculating the minimum acceptable. We start maintenance when it's either 2 or 5 times that calculated value, and we switch off the circuit, or it's deemed to be totally unserviceable and unsafe to work on when it is half that calculated value. So there were some guidelines that has been given, but as you say, Steve, it is a subject which is ongoing, isn't it? Hmm?
Yeah, it's they've changed the values slightly, Keith. You've got
Yes.
MOD now. You've got a safety datum level, which is when you turn it off. When you start investigating, it's 10 times that. And then they also have a maintenance level, which you should be looking for when you calculate a new circuit. I mean, that's in that new document. Yes, it's been going a while, but that's the document everybody refers to. Interestingly, the insulation resistance values for new circuits have gone up tremendously in the last few years. I mean, we used to think if we got anything in the meg ohms, it was really good in the 80s. Nowadays, people are achieving gig ohms, 10 to the 9 regularly. And there are some circuits out there now that are in the tera ohms, which is, incredible, really, to think we can get insulation resistance values that high. So we're improving the top end, so we ought to be improving the bottom end as well.
Correct.
Okay, thank you, Tony. You've seen electrical safety, through the ages, and seen the developments in safe working practices. What's your take on this topic, please?
My take is that it's not an area where my research took me very much. I didn't do any research on this, but that's the value of having people of different competencies in the discussion. Because in developing a new equipment, I always said there were 3 people involved. One was the end user, and others the pilot, what you were trying to give him. There was a scientist who was trying to develop whatever, a suitable method of doing it. And then there were the engineers who have to implement it. And they all have their areas of expertise. Mine was in the second one, but very much saying when you've got a project, all 3 people need to be at the table equally represented, and know clearly where the responsibilities are. It isn't my responsibility as a scientist at the top level to think about the safety of the installation. But having said that, yes, safety in terms of, am I giving the pilot something he can do his job safely? Yes, that's very much an area that I have to work in. But the sort of safety areas we're discussing out today, I have had to assume and have assumed and haven't been let down that competent engineers deal with that totally and adequately. And I think that's what today is about. That area, it isn't prime assume one of those 3 areas. They all have to work together and at a high level to get everything in place, to get a safe and regular operations at all times at airports.
One of the things I said, Tony, one of the things I've always experienced going around into on airports and doing audits maintenance audits, etc., is the commercial pressures that come from the airport senior or the executive management. And I think that is a key issue. Steve, you know, we've spoken about processes and procedures. We've identified and we look at the products to ensure we've got the safety, as much safety built in terms of, you know, that the output disconnecting device, of course, was one which has occurred. But commercial pressures is a big issue.
You've highlighted that a number of times this afternoon. The pressure that can be put upon you by air traffic or behind them management who don't want to close the runway, and that, you know, one of the reasons, of course, why MARMS exists. That pressure to actually be able to monitor in an effective, efficient manner is absolutely crucial to the whole operation. And so you need a MARMS to be able to do that and have a proper monitoring.
Thank you, Tony. Keith, could you move on to the next slide, please? Just before I know time is running short. Just to let everybody know that the next webinar will be on the topic of Airfield CMMS, which is computerized maintenance and management systems. As you know, we have our own, the MARMS engineer system, but we'll be talking about this topic generally and the importance of being able to schedule, manage and monitor your maintenance, to gather the information. It's a requirement in your of ICAO, of FAA, it's in your airfield manual, but in order to do your work safely, competently, effectively and efficiently, you need a CMMS. Gone are the days of paper recording. It's just not efficient or effective enough. But if you could just drop down this last. So I look forward to seeing on the 25th of October on this at the same time, 2 o'clock for 1 hour, when we will be covering this topic in more detail. Keith, if you could just drop this slide now so we can see the panel. I have a question here following on. It says here the IR on some of our circuits is very low. Is it safe to work on these circuits wearing PPE?
I'll answer that. The answer is no. Simple and straightforward answer. No, it is not safe to work with utilizing PPE. PPE is an additional safety piece of equipment. And Steve, I'm sure you have a comment to make about that as well. Hmm?
Yeah, I agree with you, Keith. It's PPE is sort of the thing that people say, oh, well, we're all right because we've got the rubber gloves and things. No, make the system safe.
Correct. 100%.
It says here, a question from Bernardino. Sir, if the secondary cables are open circuited, is it possible the control voltage might hurt the technician?
Yes, because what happens when the secondary circuit is in open circuit, the transformer goes into saturation, and therefore the voltage on the secondary coil, secondary winding is going to be at the voltage of the primary winding. And therefore, then there is the potential of getting electric shock.
I have a question here, which I just saying that, and let me start to answer this, Keith, before you jump in or anybody else. It says, do you know of any splice kits work better than others? Well, it's very important that in our role at TMS and MARMS, we pride ourselves on our independence. So we can't get, we can't express any commercial preference over any particular make or manufacturer. I think the best thing is you need to research the market and ask your colleagues and people in the industry. I think that's all we can say really on that matter, because we often get asked which lights are best and which manufacturer and the like. And really, we are independent. We try to help the industry be the best it can possibly be. We won't get involved in commercial decisions between the various providers.
Sorry, Robert, without interfering or whatever on that thing, all I would say is if you're going to go for a splice heat shrink kit, you want to get the double insulated ones with 2 heat shrinks, because they prove a lot better than the traditional ones where they were only using 1 heat shrink. So
thank you.
Yeah, so that's worth looking for.
I think that's fair. Thank you for that. Thank you for that.
There are some good suppliers of connectors, because the connectors themselves, of course, are designed to be watertight, but many of the different suppliers, the competent suppliers, then have their own methods of doing that in their design. But so there are a range of good, competent connector suppliers in the marketplace globally. But remember, when things are new, then you can achieve the ultimate. But of course, where do they live? They live in the ground, in transformer pits, etc. And over time, products deteriorate. And it's that period of time and the deterioration rate that is the problem. And it can come back to the installation technician if they have not followed the guidance of correctly installing, fitting and installing those connectors.
Yes, it's training, competence and training are absolutely key in this area. Has to be done properly. And again, avoiding what I see in the field is very often the pressures on the people doing the job at the end. It's at the end of the cycle. There's a flight check planned for the following morning. The airport has to be opened, and people are sitting in very imperfect conditions in pits, working, trying to do these connections. And these are the factors that contribute to long-term shortfalls in the system.
Correct.
Times for two quick questions. We'll try and answer quickly because we're over time now. Another question from Nick. He said, between LED and halogen light fixtures, which one would relatively withstand an installation imperfection in relation to thermal inertia? Would bad connectors and slight faults deter a circuit from being operational? How does the CCR cope with these situations?
Well, I think to answer to Nick is that you've got to look at an LED, and you've got to look at a tungsten halogen lamp, for example. A tungsten halogen lamp is a coil in a gas enclosed in a receptacle, and but an LED is an electronic component. Now, electronic components are going to be highly susceptible to external influences. For example, external electrical influences like lightning, indirect lightning strikes, etc., or induced TMS. So we can't answer that question fully, within the webinar, but it is something where when we've looked at the merits, and there's a lot of still 10 years after the introduction, 10 or more years after the introduction, there's still discussions on the merits of LED as opposed to tungsten halogen, and it's ongoing. And so for Nick, I would say, really, when we're looking at the power unit, going back, because the second part of that question was about the CCR. Now, the CCR, of course, the technologies have changed there. So we've been traditionally in the international theatre, we've had the thyristor-based CCRs, but now we've got IGBT transistor-based CCRs, commonly known as low harmonic units, and that in themselves are different. So do you attach an LED new technology light fixture to a thyristor base, or do you change them both together so you have a IGBT CCR and an LED, or as an IGBT CCR is okay for tungsten halogen. So there are these interface issues that exist. And one of the interface issues is, of course, the light fixtures and the CCRs use pulse width modulation technology. And it is that area which has created a lot of discussions and is ongoing.
Thank you. And then Seraphin has asked a question, a suggestion. He says, there is a possibility that two circuits are powered by two RCCs by being accidentally crossed and repowered, even with one of the RCCs switched off, even having too low voltage on the primary of the RCC transformer turned off. For this reason, when in doubt, especially in works, all the RCCs that have series circuits that could share a path must be disconnected. Is this right?
I would say yes, that is correct. You know, if you go into a transformer pit and there's multiple circuits going through that transformer pit, these cables are potentially underwater, you know, in the manhole, etc. And depending on whether we have screen cable, primary cable, or on-screen cable, then when current flows through a conductor, it sets up a magnetic field. It's an AC current that is throwing, so their magnetic field is building up and collapsing, you know, at 50 times a second or 60 times a second in the US. And that will potentially induce a voltage into a cable adjacent to it. Now, when it's a screen cable, then we earth down that screening to help protect from that situation. But in the US, for example, the US use on-screen cable. So they are potentially more prone to that crossfeed. So you could have a power unit switched off for its circuit, yet some lights in that circuit have power on them because of crossfeed that is induced EMS from an adjacent circuit. This does happen.
Right.
Yeah, I think looking at his I think looking at his question, he's talking about where you've got interleaved circuits and the possibility of them actually being connected together, which has been known to happen. If you get sort of rodent damage and things, you can. So the recommendation is always, if you've got two interleaved circuits, turn them both off. You may only isolate the one you're working on, but the other one should be turned off.
Yeah.
And I promised the last question, but there's one more here. Sir, if you still have time, can you explain what is happening in the CCR during the time we change the steps from 1, 2, 3, 4, 5, etc.?
There are times constant in the design of the IEC standard, the 61822, on the changeover. So we can't go into the detail, but there is a time constant associated with between steps, and the time constant associated with the stability of the steps. So you're going from 6.6 down to 5.2, for example. So there is a time frame associated with the stability. But that's in the IEC 61822, which is the design specification for CCRs.
Thank you, Keith. And thank you, Tony. Thank you, Steve. Thank you, Felicity and Damon, for your support with making this happen. This is the end of today's webinar, and I'd like to thank you, the audience, for participating with us. It's really much appreciated. We have the next webinar on the subject of CMMS on the 25th of October, same time, 2 o'clock, same place. So we look forward to seeing you then. But before I go, if you have any training needs whatsoever, please do not hesitate to contact Felicity. Her details are on our tmstrainingsolutions.com website. And Keith and the team would be delighted to provide you training, in-depth training on competency and learning on the subject of all aspects of airfield ground lighting. So thank you for your participation. Thank you for being with us today.
I would like to say just one thing before you go, Robert, is to remember when you make a decision out on the airfield, make sure that that decision, you are happy to stand in a coroner's court and justify that decision.
Yeah. So so ultimately it is the aerodrome operator's responsibility to ensure the designers, the systems installers, the people that do the commissioning, do the operations and maintenance and management of the AGL system are competent and operate safely and safely discharge their duties. However, ultimately, I know that's true, but you are responsible for your own safety. Make sure that you are competent, that you understand what you're being asked to do and how to do it, and stay safe, because as you've seen there, accidents aren't frequent, but when they are, they can be fatal in this very, very dangerous constant current circuit environment. So be safe, and hopefully we'll see you again next on the 22nd of October for our next TMS Tuesday. 25th. Yes. Sorry. Okay. Thank you very much. Have a nice month. Bye bye.
Ciao, everyone. Ciao.
Bye.